look at and sort of quickly review the receptor types. You will be expected to know their second messenger and their effect on their tissue. So where they're located, their varying affinity, their second messenger, and their effector tissue. So just to review that here. So alpha-1 receptors and alpha-2 are mostly on vascular smooth muscle. So the smooth muscle that lines blood vessels, this is typically where we find these. They both have a preference for norepinephrine over epinephrine. Now, their second messenger is going to differ entirely. Alpha-1 is the unique case in that alpha-1 only has the IP3 and DAG as second messenger, inositol triphosphate and diacylglycerol. So both of these are the second messengers engaged in the alpha-1 binding to its receptor, or alpha-1 binding or epinephrine rather. Now, this is a G-stimulatory protein, so it's going to be increasing second messenger, and that will bring about excitation to the tissue. All right. And in a practical sense, that means constriction or contraction of the smooth muscle along the blood vessels here. Now, for alpha-2, we're going to have a similar response, but a different mechanism. The mechanism here is involving different second messenger, so cyclic AMP. And because this is inhibitory to its second messenger, it's going to decrease the amount of second messenger. However, that is still going to result in an excitatory response because of what cyclic AMP will do in this specific tissue. All right, so don't conflate the response to the second messenger. In other words, whether it's G inhibitory or G stimulatory protein, don't conflate that with the effect on its tissue or its organ, right? For the beta receptors, these are all involving cyclic AMP. They're slightly different in how they engage cyclic AMP, but beta-1 is on the heart and kidneys, and this has an equal preference for norepinephrine and epinephrine. Beta-2 is on the respiratory tract mainly, but also the uterus and parts of the lungs. That will have a greater affinity for norepinephrine than epinephrine. And then beta-3 is on adipose tissue, and that will also have an equal affinity for both. Now, again, all three will involve cyclic AMP, and all three will stimulate or increase cyclic AMP as they are coupled to stimulatory G proteins. However, the tissue-specific response is slightly different. So beta-1 will excite the heart, right? So think about increased heart rate, increased contractility. Beta-2, however, will inhibit or relax the smooth muscle of the respiratory tract. So that will be an inhibitory response to the tissue. Both things, however, are desired responses when the sympathetic system is engaged, right? Faster heart rate, but more oxygen flowing to the lungs, hence the inhibitory to the smooth muscle of the respiratory tract. Lastly, beta-3 is also excitatory, and that will be to adipose tissue. Okay. Someone's asking here, should we know their locations or focus on their second messenger resulting effect? The second messenger and the resulting effect is more important, but it's also important to know their locations, right? So prioritize the second messenger response and their effect on the tissue, prioritize these two columns, and then also know the affinity. The affinity is also important, and the location sort of secondarily. Okay. All right, any other questions from this? Next, I want to review the neuroeffector junction versus the neuromuscular junction. Okay, so just comparing the results here and the signal transduction mechanism, how that signal is transferred from the varicosity of the postganglionic neuron across to its effector tissue. So we want to think about the neuroeffector junction, again, greater distance and the presence of a varicosity, which are the swellings that are found along the postganglionic neuron, as opposed to the neuromuscular junction, which has a motor neuron right? Different neuron here, and then a terminal bouton, which is the neuron ending. We also want to think about the other side of the junction. So the muscle on the neuromuscular junction, very highly folded. This is called the motor end plate, okay? The tissue for the neuroaffector junction will be different depending on exactly where, but it will not be as highly folded as we see for the neuromuscular junction. Let's talk about the neuroaffector junction and the events here. So we have the calcium entering into the varicosity, resulting in the docking of these vesicles, the dumping of the neurotransmitter here, and this can be different. So the neurotransmitter here can be acetylcholine if we're thinking about a postganglionic neuron parasympathetic side, or it can be norepinephrine if we're thinking about one on the sympathetic side. So this is going to differ. All right. As a result, the second messenger and the exact response is also going to differ, right? Remember, alpha 1 is using IP3 and DAG only, so only the sympathetic side, whereas cyclic AMP is involved in alpha 2 and then all types of beta 3. So again, only involved here for the certain types of sympathetic responses. For the parasympathetic side, this will be a muscarinic cholinergic receptor. So it can be muscarinic or adrenergic depending on the exact tissue. However, that engagement of the neurotransmitter with the specific receptor is what brings about the cellular response. All right. For the neuromuscular junction, here we have a similar sort of sequence of events. The only difference is only acetylcholine, and then the nicotinic fast receptor is the binding on the motor end plate, and then that results in the end plate potential, which is a specific type of action potential on skeletal muscle. Okay. So just the main sort of differences between these two types of junctions and the neurotransmitters and receptors that will be engaged. Right, that's also very important. Okay, so that sort of sums up everything from the first two units. Okay, so the structure of the muscle, the cross-bridge cycling, the events of excitation, contraction, coupling, and then lastly, the factors that affect force generation, okay? And the types of twitches. We're gonna talk about all of that as well. So let's think about the structure of the muscle first. We wanna remind ourselves of the various staining patterns here. That's gonna be very important. So the I band being thin filaments or actin only, the H zone being thick filaments or myosin only, and then the A band being the area of overlap. So the distance of everything else changes except the A band. The A band is not going to change because the filaments are sliding sort of past each other. So the A band is the only region that stays the same. We also want to think about the involvement of the Z discs when the sarcomere shortens. So as we have cross-bridge cycling and we have myosin dragging actin towards the M line, the Z discs, which are the boundaries of the sarcomere, will eventually move closer and closer together. All right. So definitely go over the staining patterns here, what is forming what zone or band, and then how those things are moving closer together. Now, if we sort of zone in on cross-bridge cycling, that is also important, the events that are found here. So thinking about the two states of the myosin head, the high energy form, which is when it has ADP bound to it. It's going to go back here. High energy form, it has ADP and phosphate bound to it, versus the low energy form, which is when it has ATP bound to it. It's really important to think about these two forms in order to make sense of the cross-bridge cycling. So in the high energy form, the myosin head wants to bind to actin. Also, synonymously, we also have the calcium binding to troponin, which is making the myosin heads available for the myosin binding sites available for the myosin heads to bind. So both things are happening simultaneously, right, together. We have the myosin head now binding to the actin, and now we can sort of begin the first stage of cross-bridge cycling, which is the engaging of the myosin head with the spots on actin. Now we have the phosphate moving off, and then we have the power stroke, which is where myosin drags actin towards the center of the sarcomere, or where we have the M line. Now, after the power stroke, the ADP is also released off. However, we're not going to return the myosin head back to its low energy form until we bind a new ATP. So even though the ADP has come off, the phosphate has come off and been utilized to power the power stroke, we still don't have a new ATP, so it's going to stay bound tightly to the actin. This is called rigor, right? When the myosin head is not having a new ATP bound, so it cannot properly re-enter its low energy form, and it's going to stay tightly fixed to actin. And we talk about how this was important for rigor mortis, which is the state of muscle contraction post-mortem. Now, when that new ATP comes in, we're going to have myosin go back to its low energy form fully, and then we're going to have the detachment of the myosin head from actin, okay? And that cycle will start over and over again. And each time, it's going to engage a different spot on actin and drag it closer to the M line. So it's going to move further away, bind to actin, drag it, disengage, bind to a different spot, drag it again, and that will shorten the sarcomere over repeated cross-bridge cycles. Okay. Any questions from this topic? I'm going to move on to talk about the excitation-contraction coupling, which is also important. Okay, so the events that take place here are also very important, and the overall picture of connecting the neuromuscular junction and the somatic nervous system to the muscle contraction and the involvement of calcium release. So we start with acetylcholine being released. This is the neuromuscular junction that we described a bit earlier, highly folded, the motor end plate, nicotinic receptors only present here. And now we have stimulated an end plate potential. This is going to move down the muscle, especially through the T-tubules. So the T-tubules are these invaginations that allow this contraction to get through the muscle very quickly. Now we're going to have calcium be released because of the ryanodine and DHP receptors. There are two receptors that are coupling the T-tubule on the sarcolemma with the sarcoplasmic reticulum membrane. So those two receptors are sort of voltage sensors, and they're going to pick up that action potential and encourage calcium release from the SR into the sarcoplasm. From there, we have calcium binding to troponin. So there are two regulatory proteins on actin. One is troponin, which is the pink protein, and one is tropomyosin, which is the purple protein. So the pink protein binds calcium and then causes tropomyosin to shift away from the binding site, which allows cross-bridge cycling to happen. And then in order to cease that contraction, calcium is pumped back into the SR via the calcium ATPase pumps, and then the myosin sites on actin are going to get covered up by tropomyosin, and that will block any cross-bridge cycling and allow the muscle to relax. So those are the events of excitation and contraction coupling, right? And just think about those terms. The excitation of the muscle and the contraction of the sarcomere are coupled, especially by the way of the receptors, the ryanodine and DHP receptors. Okay. So just to quickly point out where those receptors are. I think we passed it somewhere along the way. Okay, maybe not. Let's look at the types of twitches quickly here. and the phases of the twitch. So let's start with the phases of the twitch here. So the latent period, very important. This is when force generation is starting. I'm sorry, let me say that again. That was incorrect. This is when we have no force generation yet because the machinery for the contraction is warming up. So this is a lag time that allows for the process we just described: excitation, contraction, coupling. Then we have the actual contraction phase, and this is where force generation begins. So this is when tension is going to start rising as the sarcomere has begun shortening, and we're now exerting force or tension in order to overcome the load in question. And then the relaxation phase is going to be the longest phase. This is when the force or tension slowly drops off, and the mechanism behind this is the removal of calcium from the sarcoplasm with the help of the calcium ATPase pumps. So all of the mechanisms that we just described a few seconds ago directly translate to the phases of the muscle twitch, okay? Now, in terms of the types of twitches, also important to think about isometric, where the load is greater than the force released and the muscle length stays the same, versus isotonic when the load is less than the tension released from the muscle, and the muscle can actually be lift the load in question, and so the force generation will level off when it is adequate to overcome the load. So here, the tension is the same. In isometric, the length is the same because we cannot actually overcome the load. So these two types of contractions are important as well. And then the last bit of things I want to review here are the factors affecting force generation. Very important to think about the factors. So one is the frequency of stimulation. If we increase the amount or the rate rather, how fast we fire action potentials to the muscle, we can increase the amount of force that is generated. And the first mechanism of this is trap, where there is complete relaxation in between. The second of this is summation, where there is not complete relaxation in between. In both instances, we're going to generate more force the faster we stimulate the muscle. The other effect is the diameter. So the more filaments we have, the more diameter, the thicker the diameter of the muscle, that will also increase force generation. And then the fiber length, whether the muscle is at its optimal length or not, will determine the maximum force generation. If it's too long, it's going to generate less force. If it's too short, it will also generate less force. So the length is another factor. And then lastly, we want to think about recruitment as the fourth factor that influences force generation. So with recruitment, we can start with the smaller units, which are attached to smaller neurons, et cetera, first. And then we are going to recruit or call on larger units attached to larger fibers, larger motor neurons, a greater amount of fibers, et cetera. And we recruit those to generate more force last. Okay. All right, so definitely go over all of that, especially those sort of main points that we just highlighted. And for the endocrine system, don't prioritize the endocrine system. I want to be 100% transparent. I would only focus on the levels of the axis. So definitely go over what hormone is secreted from the hypothalamus versus the pituitary versus the tertiary endocrine gland, and know the different axes, right? So TRH, TSH, thyroid hormone, CRH, ACTH, cortisol. So go over that table that we drew out, and that is probably the most important thing that you would need to review for the endocrine system. Okay, and then the final topic again is going to have slightly less questions just because we just completed this, but this is going to be the types of muscle fibers. Okay, And this summary table, you guys can see my screen here. This summary table, I think, is the most comprehensive way to review all of that. So know your three fiber types: slow oxidative, fast oxidative, fast glycolytic, and know the various properties of each. Which of these is going to generate the most force? This is going to be your fast glycolytic because the fibers are larger here. They're reliant on glycolysis, anaerobic glycolysis. They're not reliant on um, uh, oxygen or mitochondria or diffusion through capillaries of that oxygen. And so they're going to have a bigger diameter. They're going to generate more force, and they're going to be white in their appearance, right, on histology. We can also think about resistance to fatigue because they're larger and they generate more force and they build up lactic acid because of anaerobic glycolysis. They are going to be low resistance to fatigue. Okay. Other features of fast glycolytic would be their motor unit size. So large motor units, again, makes sense because they have larger diameter, et cetera, et cetera. Comparing that on the other end to slow oxidative. These are going to have a high oxidative capacity, meaning that they're reliant on oxygen. They're going to have a low glycolytic capacity, so fewer glycolytic enzymes will be required here. They're going to have a slow speed of contraction and also generate less force, right? This makes sense because they're smaller in diameter. So because they're smaller in diameter, attached to smaller motor units, generate less force, smaller fiber size, etc. And then as far as their reliance on oxygen, that means they're going to have mitochondrial density, so lots of mitochondria, capillary density, lots of capillaries to bring that oxygen in, myoglobin, which is the storage of energy or storage of ATP in muscle, in mitochondria. And so myoglobin content will also be high, which is also going to give that red appearance to these muscles. However, they will be highly resistant to fatigue because they have a slow contraction, they use oxygen, which is a steady supply, and they do not have lactic acid buildup. They will have a high tolerance to fatigue. Okay, so go over this summary table, or if you've made a similar one, and that should be adequate to compare and contrast these various fiber types.